welcome to the course. We are going to continue on talking about how we can do the MEM simulation with COMSOL multiphysics. I am Uttam Pal. I am working as an application engineer in COMSOL multiphysics, and today we are going to talk about MEM simulation, that is piezoelectric devices. We talk about piezoresistive devices, fluid structure interaction. We will talk about sensors, different types of sensors and actuators. So let's go forward. Earlier we have already seen different kinds of sensors and actuators and piezoelectric devices, piezoresistive devices. So what we are going to talk about now is a demonstration of a particular actuator, as you can see over here. So what you see over here is the following. This is a thermal actuator. The name actuator stands with the purpose that we will need to give it a particular voltage, and it needs to be converted, or the electrical energy that is given through the voltage needs to be converted into a mechanical energy, a different form of energy. So the voltage that we give over here is through anchors that you can see over here. These are the 3 anchors, and based upon the current that is flowing through the space. So if you confine the space of the flow of current, it actually creates more heat energy as compared to a space which is not confined, right. So over here you can see that the space over here is like very much confined. You need to give a voltage over here and you ground this particular anchors. So top anchor you give a particular voltage and you ground the bottom 2 anchors. So the flow of current will actually be from here, it will go like this, and then it will be divided into 2 parts over here in the second from the top, and from the third, that is the cold arm over here. So the current will be getting divided into 2 arms, and the most of the heat energy that would be dissipated would be in the top arm that you can see over here. The heat which is getting dissipated will also lead to thermal expansion. So over here there are 3 physics that are going to be involved. The first physics is the electrical currents, that is the current that is flowing through all the arms. The second thing is, because of the Joule heating there is a rise in temperature, and because of the rise in temperature within the arms, 2 hot arms and 1 cold arm, there is a thermal expansion. The thermal expansion takes place in such a manner that it allows your device to move in a single direction. That direction is defined by the structure that we have made. Over here also, if you imagine that the top layer is expanding, okay, and what we are assuming is that these 3 anchors are having a fixed constraint, that is, it cannot move in any direction. We give on these dimples, so this is the first dimple, second dimple and third dimple, we give roller boundary condition, that is, it can allow the motion only in tangential direction, not in normal direction, okay. So this dimple will allow your movement only in the tangential direction of its surface, not normal direction. So it cannot move up and down, but it can move laterally. So if you assume that this arm, that is the top arm, is going to expand, thermally expand, so then it will actually move toward the lower side. So that is what we will see how to set up this particular model, how the deformation is going to take place, how much deformation is going to take place, and finally try to understand, if we are talking about a particular material, what is the maximum temperature that it can take place, or the maximum input voltage that it can take before the structure actually breaks down. So let us go to the next slide, that is talking about the 3 different physics boundary conditions that we give. The first is the electrical boundary condition, that is, we apply the voltage on over here, these 2 boundaries, and apply a ground over here. So the current actually flows from the bottom over here to the top, and then we apply fixed boundary condition on these 3 anchors, and then roller boundary condition on these 3 dimples. So this is my structural dynamic properties, and then finally my thermal properties are that I fix my temperature at the dimples and the anchors, and the remaining boundary I apply a convective heat flux. If the temperature is very high, you can also apply radiative heat flux. So, let us go forward and open COMSOL. So, if you open COMSOL, this is the first screen that you will see once you open COMSOL. In this case, I need to actually first make so the approach that happens with any simulation tool, any FEM simulation tool, is that you first make the structure or the geometry. The next is that you apply the materials to each of the domains of your structure. The next is to apply the physics boundary conditions, that is the third part. The fourth part is to mesh the complete geometry, because the numerical algorithm that is going to take place is not going to take place on the geometry, but it is going to take place on the mesh nodes. All the mesh nodes, that is the complete structure, the complete geometry, you divide into very small elements, that is known as finite element method. Once you create the mesh, you perform a particular kind of a study, that could be a stationary study, or in other words steady state analysis, that as time t equal to infinity, that as time goes to infinity, what is the final state of your system, that is known as stationary analysis. If you talk about harmonic analysis, that is you are trying to excite your system with a particular frequency, then it is a frequency domain study. If you are talking about a transient simulation of your system, that is you want to know how your system is behaving in a transient manner, that is time dependent simulation, is also can be performed. And then finally you post process the results. So, this is the one step by step process that we will take today to understand how to make a actuator. So, let us first go to model wizard, and COMSOL is asking me of which space dimension you want to select. Do I want to make a 3D geometry, do I need to make a 2D axisymmetry, or 2D, 1D axisymmetry, 1D or 0D. As of now we will make a 3D geometry. So, let us go to 3D. So, now as you can see over here, as of now we will go for a 3D space dimension. So, let us go to 3D, and then COMSOL is asking me about what kind of study or what kind of physics you want to solve. So, you can see that in COMSOL there are many different kinds of studies or physics. You have AC/DC studies where, or physics where you can do magnetic fields, electric field simulation. As of now we will go for structural mechanics, and in structural mechanics we will go for Joule heating and thermal expansion. So, once you click on this particular physics, you will see over here what does the physics talks about. It talks about different physics that we are solving for. For example, it first talks about electric current interface, that is it will solve the currents, it solve for the Poisson's equation, the current, Ohm's law. Then the second is the solid mechanics, that is it will solve for the deformation of your geometry. Then the third part, it will solve for the heat transfer equations, that is it solve for the convective heat flux, conduction, and all this type of analysis it will solve for. So, once I click on this Joule heating and thermal expansion, I click on add. Once I click on add, you will see that all the interfaces are added, that is it solve for solid mechanics, then it will solve for heat transfer, and then finally electric currents, these three physics. And on the right side you will see the dependent variables. For example, in solid mechanics the dependent variables are the displacement field variables, that is u, v and w. U talks about the displacement in x direction, v talks about the displacement in y direction, and w talks about the displacement in z direction. And this field variable would be solved for each node, mesh node each mesh node. Similarly, for heat transfer there is only one dependent variable, that is T, and for electric currents we solve for only one dependent variable, that is V. So, in total there are 5 dependent variables that we are going to solve for. In addition to it, we know that our problem is a multi-physics problem, that is once we pass the current there is going to be Joule heating. To take that into consideration, we apply electromagnetic heating, that comes under the multiphysics node. And then we also have thermal expansion node, which couples the heat transfer interface to the solid mechanics interface. So, next I go to my study and click on study. So, then COMSOL is asking me about which kind of studies do you want to perform. Here you will see many different kinds of studies. As of now, we will go for only stationary type of a study. Okay. So, I just double click on the study stationary and click on I do not want to save my earlier file. So, I click on OK. So, the example that we are talking about, thermal actuator, is already available in the COMSOL multiphysics application library. If you want to search over here, you can just search. So, for example, you can go to file and application library and then search thermal actuator, and once you click on search, you will see the example model that we are going to do. It is this exact same example model that we are going to do from scratch. So, for example, once you search for this in application library, you will be shown around 4 to 5 examples, different types of analysis that is performed on thermal actuator. You can click on open PDF document to know the theory part. So, you can see this is the documentation and it talks about the theory part, what kind of material properties we are giving. The different kinds of physics, the results, and the step by step process to make the complete model is also available. Okay. So, if you want to make from scratch, you can also do it by watching the PDF documentation, and if you click on open, the model file, the model file which is already made will be open, right. So, you can see over here you have the geometry, the way to make the geometry, then we have the materials that we have applied over here, and then we have the electric currents interface, heat transfer interface, multiphysics node, and then the meshing node, and then study and find the results. If you want to see any other model files, you can also see that. For example, you can in the structural mechanics module, we have another thermal actuator TM model, which is the parameterized approach to go forward, that is also available over here. Over here we have used polycrystalline silicon material. In our case, we can use the polysilicon. So, let us go forward and start the model from scratch. So, the first thing, as you know, we have to first make the geometry. One approach to make the geometry is using the tools available. So, if you right click on the geometry, these are the tools which are available. You can use this approach. Alternately, what we will do to save time, we can also insert the sequence of geometry or import the geometry from some other COMSOL file. This is what we will do today to save the time. So, I right click on the geometry, I click on insert sequence, and then I just open the model file. So, by using the model file, I can also create the geometry. So, as you can see over here, none of the physics settings or the study or results have been imported, only the geometry file has been imported. So, first what I do, I first make the geometry using the work plane. So, this is the work plane that we have created, that is a 2D plane that we have created of the actual thermal actuator. So, this is a 2D plane, and then we do an extrusion of it in the third dimension. Okay. And then to make the anchors, I again create one plane, that is again I make a 2D plane, as you can see over here. So, this is a 2D plane that is using work plane, then I again extrude it in third dimension. So, this is the geometry that I have made now. The next part is to actually assign the materials, right. So, this is the approach from top to bottom. First make the geometry, then assign the materials. Third is to do the different kinds of physics, then the multiphysics node, then the meshing, study and post processing using the results. In the material section, to add the materials, I just right click on the materials, add material from library. If you add material from library, you will see many different material properties that are already available. This in built in is the most common materials which are available. So, you have alumina, aluminum, copper. So, as of now, let us select polysilicon. Just double click on polysilicon and that material would be added. So, you can see now that polysilicon have been added in our material section, and if you see over here, the conductivity, that is the electrical conductivity of polysilicon, is sigma of T, and the sigma of T, that is the electric conductivity as a function of temperature, is not a constant value, but it is a function of temperature. So, once you go within the basics node and the analytical sigma node over here and you click on plot, you will see how this conductivity, that is electric conductivity, is varying as a function of normalized temperature. Okay. So, as you go on increasing the temperature, if you go on increasing the temperature, your conductivity is decreasing, which also makes sense because there is more collision, which results into more heating as compared to the flow of electrons. Then we have coefficient of thermal expansion. These all material properties are very important because maybe you would be using some other material, not just polysilicon, but you would be doing some kind of research where you are fabricating your own device, maybe an alloy for example. So, in that case this material properties will change. If you want to have your own input, you want to give your own input of your material properties, you can just right click on the definition and go to the function interpolation, and in the interpolation, instead of data source as local table, you can change it to file and click on browse, and you can import any of it like .txt file or .xls, .csv, .dat file. You can import it and assign a particular material property to your material. As of now, let us delete the interpolation function. So, we have coefficient for thermal expansion, and then we have heat capacity at constant pressure, that is Cp, then we have relative permittivity, then we have density, thermal conductivity, again a function of temperature, and this is again a scalar value. For example, you want to change the relative permittivity from 4.5 to maybe 5 for example, you just need to double click on that and just change it to 5 for example. You can just click on it, make it 4.5 for example. So, it is very flexible to change the material properties, and it is very open software. As you can see, you have also Young's modulus, which you can just double click and change if you want to maneuver to your own material property, and it has a Poisson's ratio of 0.22. Okay. So, the next thing is to apply physics boundary conditions one by one. So, the first thing is to apply the electrical currents interface. Now, over here if I want to apply the boundary condition, I will just go through and check what are the boundary conditions that I need to apply. So, as you can see over here, I need to apply the voltage at the bottom two anchors and ground on the top anchor. So, I right click on my electric current interface, and I have been given so many domains conditions. So, you can see the cylinder which is fully filled is a domain condition, that is it can be applied on the complete volume. In the bottom node you can see these are the cylinder with half filled, those are the boundary condition, that is you can apply on a particular boundary. Then we also have edge and points. As of now, let us apply electric potential boundary condition. So, I just select on this one, and let me just select the bottom two anchors, right. These two anchors I apply, and I give a potential of V naught. The potential V naught over here is potential that we want to apply which is parameterized. So, I go to my parameters and these are already a parameters that I have been imported once I import the geometry. The next I want to apply for the physics. So, I just right click on my global definition, I click on parameters and here I write physics parameters. These are my geometry parameters. If you want, you can write in continuation over here also, but just to delineate between different parameters, let me add a new parameters. So, let me write as 0.1 volts, that is under 100 millivolts we are going to apply. So, we have electric potential, we apply V naught. So, now you can see it is not yellow, it was earlier yellow color because it was undefined, and then we need to apply ground boundary condition at this particular boundary. Okay. So, our system is set now, we have electric potential boundary condition at the bottom two legs and ground boundary condition in the top leg, and it is always best to actually save your model file before going forward. Always good as a habit to save and make many different versions of your model file. So, I am done with the electrical conditions, that is I have applied a potential in the bottom two leg and a ground boundary condition in the top leg. The next thing is to apply the heat transfer interface boundary condition. As you can see in the presentation, what we are going to give is we are going to give a fixed temperature at the dimples and the anchors, because it is going to stick to a particular PCB or a sensor. So, we are not going to change the temperature at the dimples and the anchors. All the other boundary conditions we are going to apply convective heat flux. Conduction is taken by default. So, let us go to heat transfer. You can in each of the physics you can see, if you go to electric currents, if you open the equation, you will see the currents or the equation being solved for. If you go to heat transfer in solid, if you open the equation, you will see the equation that is being solved for. In solid mechanics also, if you click on equation, you will see the actual equation that is being solved for. The first node under each interface talks about the material model. So, here we have elastic, linear elastic material. These are all the material models. You have solid over here, and then we have current conservation over here. The first node always talks about the material model, which kind of material model you want to make. And again you can see within the material model also there would be a particular equation that is written for that particular material models. So, yeah, we were at applying the heat transfer boundary condition. To apply the heat transfer boundary condition, I just right click on my heat transfer in solids and I apply temperature boundary condition, and I need to apply fixed temperature at the node. So, I just need to, so I have my scroller, so I just click on my scroller and press my scroller and just move my mouse in front. This is how I can do a zoom in. If I right click on my mouse and keep it on the right click and just move left and right, I am able to pan. If I do a left click, then I can revolve along a particular axis, right. So, this is the basic features of the movement of your geometry in the graphics interface. Anyways, let us apply temperature boundary condition, that is at room temperature to the dimples. So, I apply to the one of it, second and then the third, and similarly on the anchors I apply over here, here and here. Okay. So, I have applied temperature boundary condition on the top of the dimples and on the top of the anchors. So, these boundaries will be maintained at 293.15 Kelvin. that is 20 degrees Celsius. Next, I need to apply convective heat flux on the all the remaining boundary condition. To apply that convective heat flux, I just need to right click on heat transfer, and again you can see these are the domain condition. Right now I want to focus on the boundary condition, that is heat flux boundary condition. So I click on heat flux boundary condition, and I need to select all the boundaries and remove the top boundaries of the anchors and the dimples. So what I do, I just click on Control A. This will make me select all the boundaries, and I can zoom in. I can again left click on those boundaries which I do not want to select. So this is how I remove the boundaries. So now I have applied heat flux boundary condition on all the remaining boundaries, and over here I can either apply inward heat flux, which I do not want to do right now, or I can apply a convective heat flux. So over here, if you enable convective heat flux, and it is asking do you want to give a user defined, or you can give an external or internal natural or forced convection. As of now I will give a user defined and the heat transfer coefficient as 5. This value gives me a value of similar to how the if a stationary air is present along the thermal actuator. Over here I can even apply the heat rate. For example, heat rate will give me a particular power, how much I want to give as an input, but right now I am talking about taking the heat from the system. Convective heat flux is a type of a cooling of your system. The source of the heat is the Joule's law, that is the flow of current is leading to the rise in the temperature. So I have applied my heat transfer conditions also. I just go to my save and click on save. So I am just saving my system. The next is to give the structural mechanics properties. Okay. So that is it for today. I hope you enjoyed the session. If you have any questions, please do not hesitate to write to us. We will try to respond to it as quickly as possible. Thank you.